Hello everyone, here in this video we're going to look at section 6.2. Part 1, we're going to see 2 days on 6.2. So what this section is going to show us is different ways of simplifying expressions. Remember, expressions is no equal signs that include radicals, which are square roots or exponents. Sometimes we'll see them expressed as exponents or other things of the nature of that. Alright, so we can simplify radicals if the product of the powers have the same exponents. Alright, so an example of that would be this. If I have 2 to some exponent and 3 to some exponent, notice that it's the n for both, so it's the same exponent for both of those. I can multiply the 2 times the 3 and then raise it up to the exponent. Alright, in a similar way, if we have the same radical, we can also simplify expressions. If we have square root of 2 times square root of 3, we can multiply the 2 and 3 underneath the radical and then take the square root of it. So these will be some properties that we use throughout this chapter. More on this is if we have any index, right, to where n can be any index here. So if the nth root of a and the nth root of b are real numbers, then I can multiply the a and b together and put it under one radical with that same index. But in order for this to happen, these would both have to be cube roots or both have to be square roots or anything other index that would match. Alright, so what we'll do here now is we'll go through and get some practice on these and see how we're doing on this. Now, when we're simplifying these, some of them have other previous simplifying rules come up, which aren't listed on these notes, but just other regular types of simplifying that you'll want to be comfortable with as well. Alright, so for this one here, this is an example of the rule we saw above. These both have the exponent of 4, so I could think of this really as 2 times 3, then to the 4th power. 2 times 3 is 6. And that would give us 6 to the 4th power. Now, if we wanted to, and depending on the instructions or what you're working on, sometimes you might do 6 to the 4th power on a calculator. Sometimes you'll leave it as that, depending on what you're working on. But it is possible to use a calculator, or if you're super familiar with your powers, you might just know it right away to evaluate that. But that would just depend on what type of problem you're working on and what the instructions ask for. Usually it's accepted either way. This one here. This is an example of they both have the same index of 5. So what we could do on this is that we could then multiply those insides together to where we could do the 9 times the 27. And when we do that, we'll get the 5th root of 243. And you might recognize that if you're really familiar with your powers. 243 actually is a perfect 5th root. It's a perfect 5th root for 3. So this is an example of when we'd be able to continue to simplify after we take that first step. Now, what's interesting about this is back in the original problem setup, we were unable to do anything with the 5th root of 9. 9 isn't a perfect 5th root. Neither is 27. However, once we combine them with this property, sometimes those terms will end up being able to be visible. Now, if you're wondering on where that came from, or if you want to view this from a different way, if you think about this logically, this 9 is 3 times 3. 27 is 3 times 3 times 3. Now, when I put all of those together, which becomes a 243, you should now be able to see why the 5th root of 243 is 3, because there's 5 3's that ended up being combined underneath that 5th root power. All right? So here on this one, this is another example of where at first I can't do any type of simplifying with the individual cube roots. When I multiply those inside pieces, Now we can take the cube root of negative 8, and it would give us a negative 2. So sometimes you'll be able to simplify more once you combine using our rules. So here on this one, we'd end up with the cube root of 27. And if you're familiar with your chart and powers, that would give us the answer of 3. All right, so moving on, this one here. Notice they have different indexes. We'll spend some time later on in this chapter seeing ones that essentially are little riddles and puzzles on how we can get things to link up with the same powers. But this one here, they have different indexes, so this is already simplified. And this will happen sometimes to where I'll give you a radical expression, and you might not be able to do anything to it at all, which trips people up because they're used to always being able to do something, but you'll have to be on the lookout. When you see those different indexes, there's nothing we can do with those. Those are already simplified. You'll see in the homework it'll list some like that, and in the instructions it'll say simplify if possible. All right, reducing radicals. Reducing a radical of any power is similar to simplifying a root of 2, so square root of 2. Keep in mind this chapter, anytime you don't see an index, we are working with a square root sign. And we saw this yesterday. This is just a little bit of a review from 6.1. You know, when we were simplifying square roots in previous chapters, we were looking for perfect squares within it. So 24 could be expressed as 4 times 6, to then where 4 is a perfect square for 2, and that 6 stays over. All right, and we can also do this on cube roots, except when you're working on it with cube roots, as we've seen in the past. You're not looking for perfect squares anymore, so I wouldn't want to do 4 and 6, because neither of those are perfect squares. Instead, what you'd want to do is you'd want to look for perfect cubes, which is why I put emphasis on that chart of memorizing those. 8 is a perfect cube for 2, and this is 8 times 3. The cube root of 8 is 2, so this one would be a 2 that escapes, still working with a cube root, and there's a 3 stuck over on the inside. All right, so you have to pay attention to your index to decide what type of perfect squares, perfect cubes, perfect fourth roots that you're looking for. All right, and the more you work with these, the better you'll get. So on this one, I'm going to do this one 2 ways, one using the perfect cube, another one using the tree diagram that we've seen previously. The fastest way of doing this one would be to recognize that 27 times 3 gives us 81. Once again, you'll get better at identifying these as you work on them more. 27 is a perfect cube for 3. So on this one, a 3 would escape. We're still working with the cube root, and there's the 3 remaining. Now, say you're not familiar with your perfect cubes. You can break these down into tree diagrams. I would pick, it's going to start off with 9 times 9, and then break the 9 down into 3, 3, 3, and 3. With our index being 3, I'm looking for a group of 3 3s. There they are. So when 3 of them group up, 1 can escape. And so that's where we're getting this 1 3 on the outside. Still the cube root. And then you can see this 3 didn't make it out. So there it is. And you get the same answer either way. It's just the tree diagram is for people who don't recognize when they've got perfect cubes in their situations. All right. So this one here, you could break a tree diagram down. I'm going to go ahead and use perfect powers, though. 32 is 2 to the 5th power. So this is a perfect 5th root for 2. So I have 2 5th root, this 2 left over. And if you made a tree diagram, it'd end up with a whole bunch of 2s. If you made a tree diagram, 64 ends up being 6 2s all at the bottom of your tree diagram. You would take 5 of them out because it was a 5th root problem, leaving you left over with 1 2, which is that guy there. All right, and so anyways, once again, you can always make tree diagrams for these. I encourage you, though, to instead work on learning your perfect powers. All right, and there's only so many. People and students act like there's just an insurmountable list of powers you'd have to learn, and that's really not true. When you start to work this and really commit to learning these, you will recognize them pretty quickly. A perfect fourth root within this one is 81. This is an 81 times 2. 81 is a perfect fourth root for 3. So this would be a 3 on the outside, fourth root of 2. And once again, if you finished the tree diagram all the way down on this one, you'd end up with 4 3s and a 2. And then you would grab the group of 4 3s, take 1 3 out, leaving yourself left over with the 2. The more you practice those, the better you'll get. So just don't get discouraged on those. You will start to recognize the powers the more you work on these. All right. So this is just a further extension upon here, what we saw yesterday in 6.1. All right, except now some of our coefficients won't be perfect cubes or perfect squares, perfect fourth roots. We'll have to instead leave some numbers behind. But the variables will work just as they did yesterday on 6.1. So for us here on the example, a perfect cube root within 54 is 27. This is 27 times 2. 27 is a perfect cube root for 3. Now, for x to the 5th power, I want to split it up into groups of 3, and then whatever's remaining. So one group of x cubed can escape out as an x. This 2 in the x squared must remain. All right, so on the outside, if we kind of follow the ends of our arrows here, a 3 made it out, 1x made it out, but what's left over in the cube root is that 2 and the x squared. And you can check that you did this correctly by looking at your inside portion and making sure there's no more perfect cubes or groups of 3. All right, nice. So when you're looking at these, keep in mind that you do need to pay attention to the index. This is a cube root, so I'm not looking for any perfect squares in this or perfect fourth roots or perfect fifth roots. I'm looking for perfect cube roots only. All right, 1 within 250 is, I'm going to keep the negative with it, negative 125 times 2. Negative 125 is a perfect cube root for negative 5. And if you're wondering, hey, why are we even able to do this? I see a negative underneath a radical sign. Well, remember, negatives can occur under odd radicals. So third root, fifth root, seventh root, negatives do work. All right. Then, for my x to the 6th power, I've got 2 groups of 3 on that. So an x squared will come out. The only thing that'll be left over here is the 2. All right, so sorry, I jumped the gun here. Let's place what we took out. We removed a negative 5 and x squared. The cube root still stuck within there is just that 2. All right, so this is just like yesterday, except now we're going to have occasionally some coefficients remaining within our index. Okay, so let's continue on and finish this side up here. This one here, 50, we're looking for square roots, perfect squares. That's 25 and 2. I could then square root the 25 as a 5. I could split this up into an x to the 4th and an x. Looking for groups of 2 there. I could pull out 2 x's out of that, so an x squared. Y to the 4th power is already perfect here. It's going to give us y squared. So we'll have a 5 that made it out, an x squared that made it out, a y squared that made it out. What's left over? the 2, and the x.